The Pearson Edexcel FM1 Further Mechanics 1 from November 2021. Let's just go straight into it. We've got a question here about a horizontal road, then an inclined one, so I'll draw the horizontal one first. Van mass 9,000. Got resistance this, speed is big V, so I'm just going to shove big V into there, and those are my resistances. I've got a work rate forward of 18,000. Of course, power equals FV. Divide by V, which is just capital V, we get the force forward is this, so we'll put that there. That's the force forward, and then we just set up F equals ma. We're working at constant speed, so that means A is 0, so we can put A as 0 in there, which essentially just means we need this equal to this. You can times everything by V here, because 0 times by V is still just 0. Don't hang around here, just put it straight in a calculator and get your answer immediately. Good, that's part A done. Part B, same question, just on a slope. So everything is exactly the same, except we also have a gravitational force, because this is non-gravitational forces acting backwards, so we also need to factor in the gravitational force. So we say mg goes straight down, we have mg cos theta here, mg sine theta going down the slope, which is this, just this divided by 21, which is that. And now we can set up that this minus that equals ma. I've put in a v as 15 into these forces, can you see? Before they were just big v's, because that was what it was. But now we know they're 15, so I've just put 15s into there. We have this minus this is equal to 900a. We can just solve that by typing all that into a calculator, use g as 9.8. We get this, divide by that, we get this. Don't give it to more than 3 significant figures. I've given it to 2. Because G you've estimated to be 9.8, so it says on the very front of the paper. But anyway, give everything to 2 or 3 significant figures at most on those types of things. Two particles, A and B, are moving towards each other at speeds that I don't know, and they're going in opposite directions. So according to my picture, V2 must be a negative number for this arrow to make sense. Afterwards, we're given more information afterwards. It's the same two things, and they're going the same direction afterwards, V and 2V. So I'll just say this direction here, V and 2V, and I'll say that V is positive, which would make a lot of sense because this is the bigger mass, so it would make sense that they're both going this way after the collision. But anyway, we have find the possible values of E, and so okay, we set up the two same equations that we set up every single time when we do this. We have conservation of momentum, so this times this plus this times this is equal to this times this plus this times this. Put that in. I'm just going to organize that up a little bit, and makes this, cancel out all the m's. And then we have E is the speed of separation divided by speed of approach. Speed of separation is 2v minus v, and speed of approach is v1 minus v2. It's always the other way around, isn't it? It's this minus this for the separation, and then the approach is the other way around, so v1 minus v2. This makes 2v, obviously, as the separation, so 2v is equal to this times this, which I'm just going to write down there. And we can solve this for v1 and v2, just in terms of the other things. So if we times this equation by e, and this one by 5, I guess is what I've done there. Yeah, it is. Then we can do this one, take away this one to find some v2s, which I think will be this, divide by 8 for this. And then if we go back to the original equations, we can times this one by e again, and this one by 3 this time to get this. And then we can add them together to get v1s, and I think that's going to be this. Now v is positive in this direction, v2 we want to be negative. We know e is positive because e is trapped between 0 and 1, which means v1 is kind of trivially definitely positive. So this one is definitely going in this direction because all these are positive, so that's fine. This one here we need to be negative, so we set this thing to be less than 0. Obviously the 80 doesn't matter, we just want that to be less than 0. Cancel out the v's because that's not 0, and we get e is less than 5/11ths, which means it's trapped between 0 and 5/11ths. Given the kinetic energy is 16% after than what it was before, well, kinetic energy is a half mv squared. Afterwards, the kinetic energy is a half mv squared because v is just v. Before, it's going to be 0.6. I'm going to put the 0.6 here. Of course, this is the before kinetic energy, half mv squared, where v is this before, for this particle here. I've put the 0.16 here because I need to times the before thing by this number less than 1 to make it smaller, because if afterwards it's 16%, that means it's a smaller number, so times this one by the 0.16 to make it smaller. Just make sure you get the right round. The half, the 5m's, and the v squareds can all cancel to give you this. Divide by 0.16. Square roots and just solve for e eventually. Yeah, you'll get e as 1/3. Find the magnitude of the impulse received by A, so this side again. So impulse is mv minus mu. Now, mv is just 5mv. mu is 5m times this, but I know what e is now, it's 1/3. So I can put 1/3 into there, like this, times the top and bottom of this fraction by 3, I guess is probably what I did, and everything just kind of falls out nice and easily. You eventually get this, which is minus 7.5 MV. Now that means that the impulse is going in this direction, which makes a lot of sense because the other particle is coming from this direction, so of course the impulse is going to be acting in this direction. But the magnitude of the impulse is just a positive number, just the size. So the magnitude is just 7.5 MV. So make sure you have that right around. If it's asking magnitude, it's just going to be a positive number. Question number 3, then we have two spheres, 0.3 and 0.5. One of them is going in with this velocity, the other one with this velocity, and they meet with their centers horizontal like this, like they always do in these questions, or at least almost always, I think. I can't recall one that didn't. If they meet horizontally like this, then the vertical component of their velocity stays the same. So this one is still going up with 2j, this one's still going up with 3j. I can just make up that the horizontal components are maybe ai and bi, like this. And now, what do we actually know? So conservation of momentum, we can just work horizontally. Conservation of momentum horizontally says 0.3 times u plus 0.5 times minus 4 is equal to 0.3 times a plus 0.5 times b. So that's conservation of momentum just horizontally. I don't know whether a and b are positive or not. I don't really care. Yeah, for now, just a and b. Sort this out, you get this. I think I've times everything by 10 to get this. And then here we can say speed of separation over speed of approach. Now speed of separation is b minus a. Speed of approach is u minus minus 4. And that's equal to e, but e is 3/5. So times that by 5, that's u plus 4 times by 3, I think gives you that. And now we can solve this for a very immediately because these match. So just do, I guess, this one take away this one, and we get this. So a is minus 4. We could solve for b, but I don't think I need to right now. I think knowing a is minus 4 is enough, because we're given one more piece of information here. Yeah, we're given one more piece of information here, which says, I think if I tried to solve for b, actually, I'd just get something in terms of u. But the other information here is that p, which is this one here, is deflected through 90 degrees. Now, what that means is that this vector, the resultant velocity, dot producted with the initial one is equal to 0 because it's been moved. The resultant velocity must be perpendicular to the initial one because that's what a move of 90 degrees means. So whether it's this way or maybe this way, it doesn't really matter. But it's been moved 90 degrees, so this dot this must be 0. Now this is just a2. So u2 times by a2, or dotted with a2, must be 0 because of this 90 degree deflection, which means ua plus 4 is 0, which means ua equals minus 4. But that means I can solve for u, can't I? Because a is minus 4 already, which means u must be 1, I think. And so we get that u is 1. So that's cool. And also we can then put u as 1 into here, and then we can solve for b, I think. And that's what I've done there. B is minus 1. So okay, now we have, I think, everything we need. Find the angle alpha. Angle alpha is how much this one is deflected by. So it initially goes minus 4, 3. Then it goes minus 1, 3, which is more like this, I guess. And we want the angle. There's lots of ways to do this. You can just do little triangles here and do tan inverse a couple of times, or just for practice, you can do dot products. Cos of the angle is going to be this dot this over the two magnitudes. So this is just using some core pure maths, I guess. Just angle between two vectors. So you get this, which is going to be equal to this, and we'll have our answer. How did we use that they had equal radii? Now, the fact that they're spheres, remember, if you, instead of looking this, like, the line of centers is parallel to the surface they're moving on. Now, right now I'm looking at this from, or at least I like to think that I'm looking at this from above. What happens if I start looking at it from the side instead, and pretend that one sphere is actually bigger than the other one? Well, now their line of centers aren't horizontal to the surface that they're moving on, which means the impulse doesn't act parallel to the surface they're on, which essentially messes everything up. Because one will be pushed sort of into the ground instead of just completely horizontally across. And so that conservation of momentum and stuff we looked at horizontally doesn't quite hold if it's not parallel to the surface, which it won't be if they're not the same. I've never seen that question being asked before, but I imagine for 1 mark you could have just baffled and not baffled. You could have just waffled, and I think you would have got the mark if you had just said something to that effect. It's marks like that tend not to be very harsh. I don't think, at least in my experience. Particle P has mass 0.5. It's moving along the xy plane with this. Have I drawn this? Surely I've drawn this. Probably not. Oh no, I don't think I have. This is just algebra, isn't it? Impulse is of course mv minus mu. I know that the initial velocity is 8 to 0, and this I can just write as minus lambda lambda if I wanted to, and the mass is 0.5. I probably haven't done this in the most sensible way, but what I said was that, and then that of course led me to just reading the top line is this, the bottom line is this, and you can just add these together and times by 2 and rearrange a little bit, and you eventually get this. So I think add them together, you get 0 equals all of this added together. I guess double it and you get 1, 1 and 8. And then how have I swapped those around to be the other way around? So I've added these together to get this plus this minus this, so that's the one with the wrong side. Oh, and then you can move the 4, yeah, it does make this, so that's fine. So b is 8 minus a. Now, next bit of information is that the resultant velocity, which I've just called ab, notice, has magnitude 4 root 10. So 4 root 10 equals root a squared plus b squared. I can just square both sides to make this. 4 squared is 16, root 10 squared is 10. And now I can substitute this into there to find maybe a. So I'm just going to put this b into there. I can find a. I've done this much more. You could have just typed this into a calculator from here, I guess, once you made it equal to 0. You get a is minus 4 or 12. Now, how do you know which one it is? Well, you just try, right? Like if a was 12, that makes b minus 4, which makes from here, that makes lambda minus 2. But you're told lambda is a positive constant, so that's not a thing. So now you say, okay, well, what if a is minus 4? That makes b 12, and that makes lambda 6, which makes a lot more sense according to the condition here. So that's actually the thing that we want. Find the value of lambda I have done. Find the value of theta. What was theta? Theta was the direction that it's now moving, I think. So if I put in that this vector here, AB, is minus 412, I can just do some tan inverse here, can't I? So it has 4 across 12 up. So tan inverse of 12 over 4 is tan inverse of 3, which is this. Now that's that angle there, of course. And we always measure angles in direction from the positive x-axis. So I just do 180 minus this, and I'll get my answer of 108.4, roughly. Good. Question number 5. So we've got a few things to do here. I'm going to put down that E here is a third, and E here is unknown. So that's a bit awkward, but I'll just write it there. I think everything else here I don't really need, so I'm going to get rid of it all. I don't think I need anything else now. Cool. Ball loses half its kinetic energy in this impact. So, okay, let's do some components then. So this is v sine theta, this is v cos theta. We know that the horizontal is conserved, so this is also v cos theta. And this here is not v sine theta because the vertical isn't conserved. The vertical uses this e thing. So speed of separation, if you just imagine this in your heads, is called u. U, which is the speed of separation away from the wall, divided by this equals e, so therefore this times e is this, so this one times by e is that one, so that's just going to be a third of that. And yeah, I think kinetic energy is just a half mv squared, right? So initially it's just a half mv squared. Now what's this speed here? Well, if I just call it v1 for instance, I'm told that if I halve the initial kinetic energy, I'm going to get the final kinetic energy, so that's where that 0.5 comes from. Now v1 squared is just this squared plus this squared because of Pythagoras. So I can put that in. This squared is v squared cos squared, this is 1/9 v squared sine squared. And yeah, I think I can just cancel out the half mv squareds here to get this. And sine squared is 1 minus cos squared, so I think I'll get that. Rearrange some more, keep rearranging, keep solving, and square root, and you get this. Now, I'm a little bit unhappy that, am I unhappy that this is going to surely either be a plus or a minus? I think I am a little bit. I think you're supposed to notice that this is clearly between 0 and 90, this angle, otherwise the whole picture doesn't make any sense at all. Like, if it was coming in this way, it would never hit this wall. So this is definitely between 0 and 90, which means cos is positive. I think that's just why you're supposed to justify that's the plus. Anyway, it then loses half its kinetic energy again on this impact. Now, we can just keep saying things are conserved. Now, the horizontal component into this impact here is this, so that's still that. And the vertical component into this wall here is that. So again, just like we times this one by e to get there, times this one by e to get there. And we don't know what e is, because e is different to what it was. But that's okay. If I just call this v2, I can set up a very similar thing. I can say, okay, well, if it loses half its kinetic energy again, that means it's lost 75% from when it started. So I think if it loses half, then half again, that means 0.25 times by this half mv squared is equal to that half mv squared. Before I do that, I think I can work out what sine and cos of theta are, though, I guess is what I'm doing here. If cos of theta is root 7 over 4, that's this triangle here, adjacent over hypotenuse. Do Pythagoras. 16 minus 7 is 9, root of 9 is 3, so sine of theta is 3/4. I think I can work out from there. Which means I can replace those values with, well, this times 3/4 is just a quarter v, and this times root 7 over 4 is root 7 ev over 4. And now I think I'm doing that plan that I was mentioning earlier. If it loses half, then half again, it's now got a quarter of the kinetic energy it had to start with. So that's the starting kinetic energy, that's the ending one. I can just put in some Pythagoras again, right? V2 squared is just this squared plus this squared. So I'll put those in. This squared is v squared over 16, and likewise here. The half mv squareds all cancel out again. I'm going to write that as 1 over 4. Put those together and times by 16, I guess. Yeah, times by 16. We can just solve this out. I'm sure you understand what I'm doing there. Good, and we get the exact value of E, I guess. We've only got, I think, is it only 2 questions to go? So here's the second to last one about a spring. Again, we've got lots of information here that I'm basically going to cut out in a second. Tan alpha is 3/4. Imagine a triangle, opposite 3, adjacent 4. 3 squared plus 4 squared is 5 squared, so sine of alpha is 3 over 5. Cos of alpha is 4 over 5, so that's going to be quite useful to me. I'm told that the friction mu is 1/3, and I think that's basically the only useful stuff in here, except for this top line, natural length 3L, elasticity 3mg. I'm going to use that as well. Okay, so what forces are going on here? Well, I've got, the spring doesn't weigh anything, right? It's a light spring. The only thing that weighs anything, you saw it from before, sorry for not explaining, but there's a mass on the end of the spring here, I believe. The other end of the spring is attached to, yeah. So the mass is here, so that's mg downwards. I hope I've got this right. It's not really going to make a difference even if I haven't, but the mass I think is there. That's what the picture seems to indicate as well. That's mg downwards, the mass is m, I think. And therefore we've got mg cos theta this way, which is important, and mg sine theta this way. I need both of these because, of course, mg sine theta is just the force due to gravity going down the plane, so that's helpful. Mg sine theta is 3/5, and cos alpha is, sorry, alpha not theta, doesn't matter, is 4/5. Now, I need this cos one because, of course, that's also the reaction force, and then the maximal friction force is mu r, so it's this times this, so the frictional force is just 4 mg over 15. What other forces are there? Well, of course, there's the tension in the spring, right, due to it being compressed. Now, its natural length is 3L, so the compression is 2L, right? It should be sitting at 3L, but it's only sitting in L, so the compression is 2L, so that's X. And the natural length is 3L, so just be careful on this formula here. Put in a 3L here, put in a 2L there, and then lambda is 3mg, and we get the force going upwards due to tension is this, which cancels down, I think, a little bit to this, I think. Yeah, the 3's cancel, yeah, sure. And so F equals ma says that this minus that is equal to ma, and cancel out all the m's, do some fractiony stuff, and we get a is this. I believe 26, 17, yeah, that's fine. Good. Find in terms of g now the speed of p the instant the spring first reaches its length 3L. Now I knew that this was to do with the work energy equation, partly because mostly because we haven't done it yet. That was what I was going to say. We haven't done the work energy equation, and FM1 is really nice in that it just asks you the same things over and over again. We haven't been asked about work energy yet, so it's going to be about that. So the work done is the frictional force times the distance that it applied for. Now, this string went from L, or the spring, sorry, went from L to 3L, so the distance is 2L upwards. So, or parallel to the plane, 2L. So the work done is this times by 2L. Which is this. Now the energy loss, there are 3 types of energy going on here. There's kinetic energy. Now initially it has kinetic energy 0. To finish with it has kinetic energy half mv squared, where v is just the thing that I'm looking for, the speed at this instant. So that's the kinetic energy gained. There is potential energy gained, and there's also elastic energy lost. The elastic energy lost, I think, is the thing I did next. Now, when it's, at the moment that it's at 3L, there's no elastic energy in this, because it's sitting at its natural length. So it loses all the elastic energy it had before. This is the formula for the elastic energy, lambda, of course, still being this. The stretch is 2L initially, and 2L is 2 times the natural length, which is 3L. So replace that with a 3L, the stretch is 2L, simplify that, you get this. And then there's also finally potential energy gained, which is mgh. Now, h is not 2L, just because it's gone up 2L here to get to its natural length. h is the vertical height gained. So we do a little triangle here. This is, of course, alpha by corresponding, and so this is 2L sine alpha. And then sine alpha is just 3/5, so that's going to be 2L, 6L over 5, I guess. Yeah. So that's going to be 6 mgl over 5. And now the gains, so this is the big loss here, minus the two gains is equal to this work done. So this minus that is equal to this work done. I can set that up. And I can solve this. The mgls don't cancel, the m's cancel. And then you move this over, you take away these fractions, you get this times by 2, and then square root, and we eventually get this awkward answer there. But I think that's fine. Yeah, I think that's good. Question number 7 then. Now, I don't really understand what the mark scheme is doing when it does this question, so I'm just going to do this question very differently to that. So apologies if you were here looking for how to do it the way that it was intended. This surface here has the direction of 1, 1. Now, the way that I thought of this was, okay, wouldn't it just be really nice if this just had a horizontal direction, right? Wouldn't it be really nice if this just went straight across like this, and this went in like this, and went in like this, and it just gave me the vector here? The reason that would be really nice is because I could just do this the same way as I did question 4 or 5, was it? Where I can just break the components up, I can copy this component, I can do this 1 times e, and I'll get this, and it would just be super easy if this was just straight flat across. So what I decided to do was use matrix transformations to transform this into this. So okay, now this here has an angle of 45 degrees to the horizontal, right? Because it's 1 across 1 up, this plane here. So okay, if I rotate that 45 degrees clockwise, I'll make it flat and horizontal, which is what I want. So I would like to rotate it 45 degrees clockwise. Now the formula book gives you this matrix formula, which is really helpful. So I'm going to put minus 45. This is anti-clockwise. So I'm going to put minus 45 in here to make it go clockwise instead. I could put, of course, what would it be, 135, whatever. I'm going to put minus 45 into here to make it go clockwise instead. Now that equals that if you type it in. That looks like a pretty messy vector. I'm just going to check that it works though first. So times this by 1, 1. And yeah, I end up with something that just goes horizontal, so that's good. Now, I don't actually want to use this matrix because it's messy. So what I'm going to do is just use this matrix. I'm just going to factor out a 1 over root 2 and just use this. Now, what that'll do is it will also stretch the entire thing as I rotate it, because the determinant is bigger than 1, but that's okay. I can deal with that later. So I'm just going to use this matrix to rotate everything. It's going to stretch it a bit. I'll deal with that later. Going to use this matrix. It will rotate this there, and it's also going to rotate this to be this vector here that I actually wanted. So okay, let's do that. Let's do this matrix here times by this vector. That gives me this, 8 plus 2 minus 8 plus 2. So that's this vector, which of course means it's just going down 6 and then across 10. I can now, because I'm in this situation that I really like, I can say that's 10, and I can say this is e times 6, as we saw earlier. E is 1/3, so 6 times 1/3 is 2, and that makes this vector here 10, 2. Now that's not the answer to v, is it? Because we're in my made-up horizontal plane rather than the actual one. So what I need to do is I need to say, okay, let's just pretend v is ab. If I were to multiply v by this transformation that I've been using, I would get 10, 2. So of course, if I just take the inverse of this matrix, times it by both sides, the inverse of this matrix is just, well, those two swap, but that doesn't mean it make any difference. These two become negatives, or swap the signs, so the negative just goes there. And then the determinant is 1 minus minus 1, which is 2. So the inverse, I think, is 1 over 2 times what I said there. And that, I think, is going to be AB. Of course, this is just 10 minus 2, 10 plus 2, which is 8 and 12. Halved is 4 and 6, which I believe is what they asked me to get. So yeah, that's one way to do it. It's not the way that they intended, but I think it works fine. So feel free to try that. What I would say at the end here is these are quite possibly the easiest 3 marks. This is the last question. These are the last 3 marks of the paper. These are the easiest 3 marks in the entire paper. So please, please, please read every question. Like, okay, impulses MV minus MU. We've done this. I think this is the 3rd time we've done this paper. They've given you V. They show that they've given you V. You obviously know U. You can just plug them in, and you just get I, and then of course magnitude, you do this squared plus this squared, which is root 2. Easiest 3 marks in the whole paper. Please read every question, because even if you couldn't do this bit, you'd get a third of the last question in like a minute just by knowing. I think Impulse is the first page of the textbook, so just read every question. I can't make that hopefully any more clear. Please read every question before you stop doing the paper.